So the equivalent circuit impedance, for example, 20 kVA. When we want to solve this type of equation, we need to gather all the information first. So the S is a 20 kVA. The ratio, primary is 8000 volt, secondary is 240 volt, 60 hertz. Transformer are to determine the open circuit test will perform on the secondary side of the transformer to reduce the maximum voltage to be measured, and the short circuit test will perform on the primary side of the transformer to reduce the maximum current to be measured. The following data are given: open circuit test, short circuit test. Have a look on the secondary side or on the primary side. It is very important. On secondary side, open circuit, V RMS. Secondary side means it do it at a 240 volt On primary side, which is 8000 volt, 8k volt. So we have a VRMS, IRMS, POC. We have a VRMS short circuit, IRMS short circuit, PSC. All are given. What they want to do, what they want us to do is we need to find the impedance of the approximate equivalent circuit. Refer to the primary side, and then we need to sketch the circuit. So have a look. The first thing is we need to find turn ratio. And then open circuit test. What we want to find? Actually, we want to find the YE. We want to find the polar form. This one. This one, polar form. First, we need to find the power factor from here. Remember, it must be always lagging. Given, given, given. Okay? Then, given, given. So I have this one. Remember the unit? And then I put in a rectangular form. I compare to this one. So this one is referred to this one. This one referred to this one. Then I have my Rx. Remember, we need to find out this one. Just now it is referred to the secondary side, which is a low voltage side. So we must put up like this. It's referred to the secondary side. RCS, XMS. Next, short circuit test. It is where is do it? Secondary side, primary side. So the short circuit test is carried out in the primary side. So it is P lah. So same as well. We need to find the Z. This one equivalent, and then this one is given. I can find my this one. Then I can find my angle. This one is also given. I can find this one. Then I put in a rectangular form. Okay. One thing the student like to do a mistake, which is they miscalculation this one. If can, try to calculate this one first to this one, which means you use your calculator, press 489 divide by 2.5 to get this value first, instead of directly put with the angle. Okay, no angle. Then since it's referred to the high or primary side, this is a R equivalent P and X equivalent P. Okay, so the question is asking us to do what? They want us to create the circuit referrer to the primary side. So we have a equivalent value for the primary side, this one. We have this one as well, but we don't have this one. So we need to convert the secondary to primary. How to convert? We use this equation. So that's why this one we must annotate it very clearly. RCS, XMS. Then we want to find RCP, XMP by using the equation A squared times RCS, A squared times XMS. A is the transfer ratio. Then we put inside this here. So usually I will just write like this lah. So this is a primary refer to primary circuit, right? So I'll write VP at vector IP vector, RCP, JX and P. Then R equivalent P, JX equivalent P. Then I'll write this one. Voltage secondary that refer to the primary side is equal to A times V secondary side. Current secondary that refer to the primary side, I'll write as a IS divided by A. So have a try on this. So now instead with a high voltage, with a low voltage, how you refer which one is high, which one is low. Then the answer is given here. Have a try. Yeah, the solution will be are given here. Have a try. Same as well, exercise 2. So you can see open circuit on the secondary side or on the primary side. Okay, have a try. Solution are here. So we'll talk about the per unit system of measurements. So why we want to study the per unit system of measurement is actually we want to solve the circuits that containing transformer can be quite a tedious operation. Because of the need to refer and all the different voltage levels on the different sides of transformer in the system is very complex. That's why we need a per unit system. Solution is we use the per unit system of the measurements. My laser pointer. We use a per unit system PU of measurements to eliminate the need of explicit voltage level conversion at every transformer in the system. For example, just now we learned how to refer secondary side to the primary side or primary side to the secondary side, and then it's quite difficult. Although in the end we just want to study the characteristic. What is the R equivalent, X equivalent, XM, RC, and then it's quite tedious. That's why if let's say we put in a per unit system, no matter which side of the reference referred, we can solve it directly. So the required conversion are handled automatically by the method itself. Because the impedance transformation can be avoided, so we don't need to transform like A square times A, and then many transformers can be solved easily with a less chance of error. So this is a significant for electric machineries and transformers. In the per unit system, the voltages, currents, power, impedance, and other electrical quantities are not measured in their usual SI units. We have no more volts, amperes, watts, or ohms. Instead, each electrical quantity is measured as a decimal fraction of a some base level. For example, how can we get a per unit? Actually, we use the actual value divided by base value of the quantity. Actual value is volt, ampere, ohms. Base value also volt, ampere, ohms. For example, 24 ohm, 24 volt divided by 24 volt, it becomes 1. Okay, this is per unit. So usually two base quantity are selected to define a given per unit system. Yeah, a system that has a lot of parameters. The problem is how can we start to convert everything to the per unit system? So there's a rule of thumb of rules. Two base quantities must be selected. Usually we select the voltage and the power or apparent power S. Then all the other base values are related to them by the usual electrical laws. Once the base values of S or P and V have been selected, all other base values can be computed easily from equation. For example, my P base, Q base or S base actually is a V base times I base. My R base, X base or Z base actually V base divided by I base. Then my Y base is I base divided by V base. My Z base actually V square divided by S base. Actually you see all the core of the equation same. Last time we studied S equals to VI, Z equals to V over I. Same, everything are the same. It's the same. So usually the series resistance of the transformer, we put it as a R equivalent per unit. Okay, for the transformer, the series resistance of the transformer R equivalent in per unit, it is about 0.01 per unit. The series reactance is a 0.02 to 0.1. the core loss resistance RC per unit. We must specify very clearly. Per unit is per unit. RC is not per unit. RC underscore per unit, it is a per unit. Then the unit must be PU. Okay. Dimensionless. Dimensionless means there's no unit. There's no volt, no I, no ampere. Okay, no ampere, no ohm. Then the magnetizing reactance XM is 10 to 40. The larger the transformer, the smaller the series impedance. If more than one machine or one transformer are included in a single power system, a common procedure is to choose the system base quantity to be equal to the base of the largest component in the system. For example, if let's say I have a two transformer connected together, then they have a few voltages, we must choose the highest voltages as the reference or the base. Now let's have a look. Directly go to look on the equation question. For example, is easier for us. Sketch the approximate per unit equivalent circuit for the transformer in example 2.2. Example 2.2 is this one. This one is example 2.2. Okay, and then use the transfer rating as the system base. So transfer rating is this one. This is the problem that we solved just now. The approximate equivalent circuit developed in the example was referred to the high voltage side of the transformer. So to convert it to per unit, the primary circuit base impedance must be found. Okay, so I have this one, I have this one, I have this one, I have this one, and then given this one. Okay, so my V1 base is 8000, my S1 base is 20k. 8000, 20k. Select two base quantity, right? So I can find my Z base. So Z base equals to V square divided by S. Then this is my base value. Okay. Then from base I convert to per unit. From base I convert to per unit. So my Z is per unit is I might use ZE divided by my base. I have my per unit. RCP divide my base, I have per unit. X divide my base, I have per unit. So the base will be the same, see? All come from Z. Then I put into this, what we call the equivalent circuit. You see 0.01, 0.06, 49.7, 12. All are in per unit. But remember, we also need to name per unit variables. Okay? Name per unit variables. So this is how we find the per unit system. Next, we'll talk about transformer voltage regulation efficiency. Transformer voltage regulation, in here we'll talk about transformer voltage regulation, phasor diagram, and efficiency. Okay, when we talk about voltage regulation, now we must think of phasor diagram. Ini memang kawan. They both are very good friends. So because of a real transformer has a series impedance within it, the output voltage of a transformer varies with the load. Output voltage transformer will vary with the load because the real transformer has a series impedance, even if the input voltage remains constant. So there's a voltage regulation. It's employed to compare the transformer. Voltage regulation is used to define how good is a transformer. So that's why we need a voltage regulation quantity to describe it. Full load voltage regulation is a quantity that compare the output voltage of transformer at no load and output voltage at the full load when the primary voltage held fixed. Which means now I have a primary connected to my AC source. Now I have secondary connected to my AC source. Okay? Let me draw here. I have a primary voltage, primary winding, secondary winding, connected to the load. Okay? This input is always fixed. Voltage regulation is compared when suddenly it is at full load, become no load, means I cut here, become open circuit. What is the voltage changing there at that instant? Which means connected to the load, suddenly I take off the load. Then what is the changes? Then then we'll see how good is the voltage regulation. So the voltage regulation of a transformer is defined as the changes in the magnitude of the secondary voltage as the current changes from the full load to no load when the primary held fixed. For example, this one. Load, suddenly no load. So the formula is like this. We use a no load minus full load divided by full load times 100%. Well, usually I will confuse this one. But in order for us to easily find this value, we need to think about phasor diagram. Usually it is a good practice to have a small voltage regulation. For an ideal one, it is a 0%, which means if now I support the output voltage is 230 volt, I take up the load, it also still maintains 230 at that time. We call voltage regulation as 0%. So, but it is not always a good idea to have a low voltage regulation. How can the voltage regulation of transformer to be determined? The transformer phasor diagram. It must be from transformer phasor diagram. When we talk about phasor diagram, we need to know the circuit, equivalent circuit. So, let's have a look. All the primary refer to the secondary. So I have a VPS, I have a IPS, I have this one, then I have equivalent secondary, X equivalent secondary, VS, IS. So to determine the VR of a transformer, we need to understand the voltage drop within it, okay, by applying voltage across this one. So this is the voltage, okay, this is the voltage. So I have a two branch, one is this one, another one is this one. So now this one I have no interested because I cannot read VS. I cannot read VS. So I just want this one. So VP over A actually is, if we apply Kirchhoff law, okay, is a VS plus minus VS. R equivalent IS, this one. This is my IS plus IS times X equivalent S. Okay, this is the phasor diagram that we must memorize. Remember, so VPS, which is here, terminal A and B, which is my VPS, actually is my VAB. So I substitute VP over A equals to VS plus IS Z equivalent S. And then my VP, so my Z equivalent S is VS plus R equivalent SIS plus ZJ X equivalent SIS. So this is the second step of the Kirchhoff law. So from the equation, VR of the transformer depends on the series impedance. This is the series impedance. Current in the transformer IS. Okay, we can see very clearly VR are dependent on these two items. Z equivalent secondary and IS secondary current. And the effect of the excitation branch on the VR transformer can be ignored. We totally ignore this one. Okay. Lastly, phasor diagram is the easier way to determine the effect of the impedance and currents on the VR of the transformer. Why we say so? Let's have a look at.